Welcome to this video where I look at ionization energies. It's important to note the definition for ionization energy, and here I have given the definition for the first ionization energy. And this is the energy required to remove one electron from each atom in 1 mole of gaseous atoms to form 1 mole of gaseous 1 plus ions. So in essence, you've got 1 mole of atoms, and the state symbol is important. They need to be gaseous. They need to be separate atoms for them to be ionized. From each atom, you're removing 1 electron, and you form 1 plus ions. Now, some definitions also include a statement referring to removing an electron from the outer shell, or the most loosely held electron. It's important to remember that the electrons in the outermost shell and also in the outermost orbitals are the highest energy, and they require less energy to remove, so they're easier to remove. If you're looking at the second ionization energy here, then you're going to change the definition. For the second ionization energy, you're going to start off with 1 mole of gaseous 1 plus ions, and then you're going to end up with 1 mole of gaseous 2 plus ions. So in this case, it's going to be the energy required to remove 1 electron from each ion in 1 mole of gaseous 1 plus ions to form 1 mole of gaseous 2 plus ions. And for the third ionization energy, you can change the charges on the ions at the beginning and the end, and so on. So when we write equations, it's very important to note that we include the state symbol. It has to be gaseous for the atoms and the ions. The first ionization energy can be written as follows. Here an example is lithium. So lithium gas goes to lithium plus gas plus E minus. That is for the first ionization energy. We've got 1 mole of lithium gas. We're going to form 1 mole of lithium plus gaseous ions, and we're going to form 1 mole of electrons there. Okay. The first ionization energy equation can also be written as this. So here we need to recall that gaseous atoms can be ionized, for example, in the ionization chamber in a mass spectrometer. And for further details, you can look at my earlier videos on this topic. So here we have a gaseous lithium atom, 1 mole of gaseous lithium atoms. Each atom is bombarded with an electron, a high energy electron. When the electron approaches the lithium atom, it will knock off an electron on the outermost orbital, the most loosely held electron. So you're going to end up with lithium plus gas, and we're going to end up with 2 electrons. 1 electron you started with, we're using that electron to ionize lithium, and the second electron has come from lithium itself. It's lost 1 electron. You can write the first ionization energy equation using either method. Either method is correct. Now, if we had the second ionization energy, from the definition I described earlier, the second ionization energy, let's say we're going to start off with lithium plus gas. And using the first example, the first approach, I'm going to go from lithium plus gas to lithium 2 plus gas plus E minus. And here we're just losing another electron from lithium, but this time we're starting with lithium plus. For the third ionization energy, then we'd have as follows. We're now going to have lithium 2 plus to start off with, gas, and then we're going to go to lithium 3 plus, gas plus E minus. And in this way we can remove successive electrons. A reminder of the periodic table, and we have groups going down. And as you go down the groups, you will increase the number of shells. And as you go across a row or a period, you will have the same number of shells, but you will increase the nuclear charge. That is the number of protons in the nucleus. And I'm going to come back to this on the next slide. So ionization energy is influenced by a number of factors. And when we answer questions on ionization energies, we need to think about these factors and which apply to different scenarios. So the most important thing to understand is that if the attraction of the nucleus for the outermost electrons is high, then the ionization energy, the energy needed to remove those electrons from the atom, is also going to be high. So here, a few factors can influence the attraction for the outer electrons. The nuclear charge. The nuclear charge is basically the number of positive charges or protons in the nucleus. Remember from GCSE and from elementary AS chemistry, you will know that each proton has a relative charge of +1. The more protons you have in the nucleus, the higher the overall charge in the nucleus, and we call this nuclear charge. Okay. If we have a higher nuclear charge, then we're going to have a greater attraction for the outermost electrons, so the ionization energy will be higher. Atomic radius. Now it's important to understand when we talk about atomic radius, we're assuming that the atom is spherical. It's not going to be exactly spherical in shape, but we just need to use this term just to approximate a sphere. So here we have a crude diagram here. I have my nucleus in the middle, which I'm going to shade in. It has the protons, a positive charge in there, as well as the neutrons, which have no charge. The number of shells will determine the atomic radius. So if I have more shells, the atomic radius, the distance from the center of the atom all the way till the end, is going to be greater. If there's a greater atomic radius, there's going to be a greater distance between the protons in the nucleus and the outermost electrons. So we're going to have a greater distance between the positively charged nucleus and the outermost electrons. Because of this distance, the attraction for the outermost electrons by the nucleus is going to change. If you have a larger atomic radius, then the attraction of the nucleus for the outermost electrons is going to decrease, and vice versa. Now, shielding is also an important thing to consider. Imagine you have negative charges, more than one negative charge close together. So I'm going to draw negative charges. Okay. Negative charges that are close to each other will repel. It's going to be the same thing for an atom with electrons orbiting the nucleus. So we put the electrons, the negative charges, in shells, or the first shell. I'm just going to put 2. I'm not going to show orbitals here. I'm just going to use a simple GCSE model of shells. I'm just going to put, let's say, 2 electrons there. So in this atom, we've got 2 electrons on the first shell and 2 electrons on the second shell. Now you can see that if I have electrons in here, electrons in between the outermost electrons and the nucleus, there's going to be electron-electron repulsion. We say that the outermost electrons are shielded from the nucleus. Because of this repulsion, there's going to be less attraction between the nucleus and the outermost electrons, so it's going to be easier to remove them. It's going to require less energy to remove them. So it's going to be a lower ionization energy. Now, if I now fill this shell up, and my outermost electron is on the next shell, that outermost electron is even more shielded from the nucleus. There's greater shielding from the nucleus of the outermost electron, so the ionization energy is going to be lower because less energy is required to remove it. So we need to consider three things when we look at ionization energy: nuclear charge, atomic radius, and shielding of outer electrons. So now firstly, I want to refer back to a previous slide where I looked at the periodic table. Now across a period, across a row, I said that there's an increase in nuclear charge because there's more protons. This is why there's a general increase in the first ionization energy across a period, because there is no increase in atomic radius, therefore no increase in shielding. The shells are the same. But the nuclear charge increases. And this is why there's a greater attraction between the nucleus and the outermost electrons. So you require more energy to remove those outer electrons. When we go down a group, and I said when we go down a group, we increase the number of shells. Firstly, there is an increase in nuclear charge, because as we go down a group, there's a greater number of protons. There is also an increase in atomic radius, and therefore an increase in shielding. Okay, so we got two opposing factors. The increase in nuclear charge should increase the attraction between the nucleus and the outermost electrons, and it should increase the first ionization energy. We don't see that. We see a decrease in first ionization energy as we go down the group. But there is an increase in atomic radius and an increase in shielding. What this does is that this reduces attraction of the nucleus for the outermost electrons. And here we need to understand that this means there's less energy involved in removing those electrons. So we have a decrease in first ionization energy. Now the other point we need to say is that the increase in shielding has a greater effect than increase in nuclear charge. So if you have an increase in shielding and an increase in nuclear charge, normally the increase in shielding wins. It has a greater effect. Now, I haven't actually put here anything about the increase in atomic radius, meaning there's less attraction between the nucleus and the outermost electrons because of the greater distance between them. You can put this point down if you wish. It depends on the number of marks that you have, but I will give you an example later, and I'll work through all the points you can mention for it. Okay. So here we've got the first ionization energy down a group. And as we have seen before, we see a general decrease in the first ionization energy. Now here, right, the decrease is more rapid, steeper gradient. Here it's less rapid, but there's still a decrease. We just need to talk about, in general, that there's a decrease in first ionization energy down a group. We don't need to talk about it in this much detail, but we need to be aware that the rate of decrease can change. Now, most of you have seen this graph of first ionization energy against atomic number. So we are going from hydrogen, which is here, to neon. Okay, that is across one period. Okay, well, actually, it's across two periods. So we're going hydrogen to helium. Okay, that's the first period. We're going from lithium to neon, the second period. Then we're going from sodium to argon, the third period. And then at the bottom, we start the fourth period. You can see a pattern here. So the first thing we need to know is that when we start a period, then we drop to a very low ionization energy. That's how we know we've started a new period. So we go from lithium to neon. Now, when you approach the end of the period, that atom will have the highest first ionization energy for that period. Okay, so we can see the similar pattern when you go across different periods, from lithium to neon, sodium to argon. We can see the same patterns. Now, I want to talk firstly about the first period, going from hydrogen to helium. Okay, and this is where I'm going to use an example, and I'm going to write this down so it's easy for you to understand. When you go from hydrogen to helium, we need to look at the subshells and the orbitals. So in the 1s subshell, we've got in hydrogen, it's got an atomic number of 1. Okay, so it has 1 proton, and in a neutral atom, it also has 1 electron. There's the electron. Okay, all right. So when we go from hydrogen to helium, right, all we're doing is we're filling that 1s subshell. Okay. Now, it's very important to understand that when we do this, we are going from hydrogen to helium. So we have an increase in nuclear charge. There is no increase in shielding. Okay, no increase in atomic radius, but I prefer shielding here. I think it's the most effective thing to say here. Okay, so therefore, there's a greater attraction of the nucleus for the outermost electrons. And I like to talk about the outermost because that's the one that's going to be removed when we talk about the first ionization energy. Okay, so here, right, we're not changing the shells. Okay, we're still in the 1s subshell. We're not changing that. So the electrons are going to be the same distance from the nucleus. There's no increase in shielding. Okay, to be honest with you, these electrons are not really shielded from the nucleus because there's nothing in between. So there's in both cases there's actually no shielding. Okay, so this is why the first ionization increases. Okay, when we go then from helium to lithium, what's happening is this. It's the same as before. We have gone from helium to lithium. Here we are starting the next shell. So lithium, this is hydrogen, this is helium, and now lithium will be this. So lithium, we can see that we've started the next shell. We've gone from shell number 1 to shell number 2. Okay, so 1s to 2s. We've gone to the next shell. Okay, so we have an increase in nuclear charge because the atomic number of lithium is 3 and the atomic number of helium is 2. So we have an increase in nuclear charge, more protons in the nucleus. But we also have an increase in shielding. Okay, which has a greater effect than increase in nuclear charge. Okay, So here, what's going to happen is we're going to have, therefore, a lesser attraction of nucleus for the outermost electrons. So it's going to require less energy to remove them. So it's going to be lower first ionization energy. Now let's go from lithium to neon. In general, there is an increase in the first ionization energy. Why is that? Because there's an increase in nuclear charge, there is no increase in shielding, and so there is a greater attraction between the nucleus and the outermost electrons, and it requires more energy to remove them. So these are the points we need to talk about. There are, however, some blips. Okay, the first blip is going from beryllium to boron, and the second blip is from nitrogen to oxygen. So here we are going from group 2 to group 3. And here we're going from nitrogen group 5 to oxygen group 6. Okay? We see these blips, we see these decreases, these small decreases in first ionization energy, which do not follow the general pattern of increase. You can see the same pattern repeated across period 3 when you go from sodium to argon, because magnesium is in group 2, aluminium is in group 3. We see the similar decrease, a similar pattern, and phosphorus is in group 5, sulfur is in group 6. We see a similar decrease. So there's a pattern here. Those blips are going from group 2 to 3 and also from group 5 to 6. Okay, so we need to understand this pattern. Okay, why is this happening? Okay, we're going from beryllium in group 2 to boron in group 3. So this is beryllium, the electronic configuration of beryllium, and for boron. So here you can see that's it's actually quite easy. I'm going to label this 2p. This is a 2p subshell. So here, when you go from beryllium to boron, there's an increase in nuclear charge. Yes. But we are still in the same shell, but in boron, the outermost electron is in a higher energy subshell. It's not in 2s, it's in 2p. So this means that there's more shielding, there's more electrons between the nucleus and this electron in the 2p subshell. So because of the shielding, there's a small decrease in the first ionization energy. So let's talk about what's happening. There's a decrease in the first ionization energy because of the following points. Firstly, there's an increase in nuclear charge. Okay. There is also an increase in shielding. Okay. And here what we're saying is the reason is the outermost electron is in a higher energy subshell. And if you really want to make it clear, you can talk about it. Let me 2p instead of 2s. Let's make it crystal clear to the examiner what we're talking about. Okay, the effect of shielding is greater than increase in nuclear charge, or the effect of nuclear charge. And this is why you require less energy to remove that outermost electron. Okay, all right. there's a point I want to highlight here. When you talk about shielding, it's best to refer to the outermost electron. That's what's being shielded. And then at the end, you always need to finish the sentence by saying that less energy or more energy is required to remove the outermost electron. That is referring to the change in the first ionization energy. Okay? This is quite important. Another thing that students often get confused with, sometimes they will think about electron-electron repulsion. They may say, for example, that if you have paired electrons, there's electron-electron repulsion, so it may be easier to remove this electron rather than that electron. Okay, so in this case here, this electron may be easy to remove it because they talk about electron-electron repulsion. This is incorrect in this case. The reason is this is a completely filled subshell. This is a 2s subshell, is completely filled. When it's completely filled, it's stable. If the 2p subshell then was completely filled, like this, then it would be completely full, it would be stable. However, if you have the situation like this, where it's incomplete, it's not really very stable, then when you have paired electrons, in this case, there's electron-electron repulsion, because in this p orbital, this is px, 2px, 2py, 2pz. In this orbital, in this 2p subshell, you can see that we have a pair of electrons. The whole subshell, the whole thing, is not full. So we can have electron-electron repulsion. Because this 2s subshell is full, the electron-electron repulsion doesn't really count. Because it's a completely filled subshell, it's stable. So now let's look at the next blip then. Nitrogen to oxygen, where I'm going to refer to that electron-electron repulsion. So here, we're going from nitrogen, which is in group 5, to oxygen, which is in group 6. And you can see the only difference is that here, in the 2p subshell, we have unpaired electrons. Here, we have one paired electron. We have one orbital with its paired electrons. This is how we're going to talk about this. So, we're going to say that there's an increase in nuclear charge because we're going from oxygen to nitrogen to oxygen. There's an increase in protons, but there is in oxygen a 2p orbital has a pair of electrons. There is now electron repulsion, and because of this, less energy is required to remove one electron from the pair. And you can see in nitrogen, in the 2p subshell, there are no paired electrons. It's very important to understand that the electrons in the 2p subshell are in normal cases, normal situations, equal in energy. So when you pair those electrons here, there's going to be electron-electron repulsion. It's also important to note that in this case, not many people talk about increase in nuclear charge. So normally you don't have to talk about this, but you will need to double check with your specification. If you do talk about increase in nuclear charge, you will also have to add the point that the effect of electron repulsion is greater than the effect or the increase of nuclear charge in this case. Okay? It compensates for and it's greater than the increase in nuclear charge. Okay, so we've gone through some points about first ionization energy. Now, another thing I want to really highlight is this. If you look at the last element in period 1, the last element in period 2, and the last element in period 3, you will see that there's a decrease in the first ionization energy. That's because all these are in group 0, we're going down the group. And we've already discussed that when we go down the group, we have a decrease in first ionization energy and why we have that. If you then look at, for example, all the elements in group 1, you go down the group, we also have a decrease. All the elements in group 2, as we go down the group, we have a decrease. And this chart shows this, but it's important to understand where to look. Okay, now when you go from sodium to argon, I'm just going to highlight that the trends are the same. Okay, so we have going from sodium to magnesium, increase in first ionization energy. And in general, there's an increase for the reasons mentioned earlier. Magnesium to aluminium, there's a little blip. It's the same reason for the blip between beryllium and boron. Going from phosphorus to sulfur, there's a little blip. There's a little decrease which does not follow the general increase, general pattern of increase. And the reasons are the same. If you look at the electronic configurations, we will now be in the next shell number 3, but for the same reasons as we mentioned earlier, we'll have this decrease. Let's now talk about successive ionization energies. So this graph shows the ionization energy and how it changes as we increase the number of electrons removed from a single atom. So here, for example, if we have an atom M, we're going to, it's a gas, we're going to make M+. That's the first ionization energy. And if we go from M plus gas, and from the ion now, we remove the second electron, it's going to be the second ionization energy. Now I'm going to draw this atom here so I can show you what's going on. Okay. So here we got the atom. I will remove one electron, the outermost electron. When I remove that, I'm going to have one electron short. So I'm going to have an overall positive charge. Okay, so it's going to be a 1 plus ion. That 1 plus ion has a higher charge density than the single atom, which is uncharged. Now think about the charge density as being roughly how spread out the charges around the atom. It's going to be less spread out and more concentrated if it's a higher charge density. It's not an easy concept to understand, but it's something which is important. For example, if you have a magnet which it has a stronger magnetic field, it's going to increase the pull of that magnet towards metal. So if you have a higher density of charge, the positive charge is more concentrated, less spread out, it's going to pull the electrons more strongly. And this is the idea that we talk about. So here, when we go to successive ionization energies, we remove the first electron, the first ionization energy, then the second, and the third, and the fourth, and so on. We increase the first ionization energy. The reason is as follows. Let's compare the second to the first ionization energy as an example to answer this. So firstly, removing an electron, and here I'm going to cross this out, removing the outermost, still the outermost electron from M plus. Requires more energy, and we're comparing removing the outermost electron from M plus to removing the outermost electron from M. Requires more energy than for M, as M plus has a higher charge density, giving it a stronger attraction for the outermost electron. Here we have not changed the atomic radius. We are still on the same shell, but what we have done is we increased the overall charge. So we increased the charge density. And this means that the outermost electron has a stronger attraction, more strongly attracted, and requires more energy to remove. Okay. Now let's look at a second point here. Imagine now I remove all these electrons. I'm going this way now. What I am left with will be this. That's going to be 4 plus. Obviously, that has a higher charge density than this original uncharged atom M. And there's two things that happen here. Firstly, we removed 4 electrons. But secondly, we have also removed the outer shell, so this now has a much smaller ionic radius. Okay, so these two factors both contribute to the increase in the ionization energy. So if I was to remove this electron here, it would actually take a much bigger increase in ionization energy to remove that electron compared to the electron on the this shell here on the outer shell. So you can see going from 4 to 5, there's a massive jump in the first ionization energy, and the reason is because you are going to you remove this 5th electron from an ion which has a higher charge density but also a smaller ionic radius. So this is how we're going to answer this. There's a big jump in ionization energy when you go from the 4th to the 5th ionization energy, and this is because the 5th electron is removed from the next shell in. It is closer to the nucleus, and so there's a greater attraction between the nucleus and the outermost electron, and it requires more energy. There is still an increase in charge density, but the increase in charge density is going to be much higher when we remove the 4th electron. After we remove the 4th electron, the increase in charge density is much higher than when we remove the other electrons, because we have reduced the ionic radius, the radius of the ion. And that's another way to explain why there's a big jump. Now, if we remove the electrons on the outer shell, we see an increase in the first ionization energy. And that's before the big jump. That's how we can tell that there are 4 electrons on the outer shell. Because we removed 4 electrons, there was a steady increase in first ionization energy. Now, when you remove the 5th electron, there's a big jump. We're removing from the next shell in. That's something we can use to tell us some information about the electronic configuration of an element. So successive ionization energies are very useful. Okay, this is another way to present successive ionization energies in a table form. Now, sometimes this can be confusing because we can't compare the increases as well as for a graph. So what I would do is I would see the fold increase. I can use a calculator or just mental arithmetic. That is roughly double increase. That is less than double, but still a clear increase. And this is less than double. Okay, there is a big increase here, almost fourfold. So I'll say roughly fourfold. I'm doing this on the top of my head. You can do it with a calculator if you wish. So if I looked at this table, I would use these kind of calculations to tell me the full increase. There's a big jump between the second and the third ionization energy. What this tells me, you have to remove the first 2 electrons before you go to the next shell. So this element is in group 2. So this tells me that firstly, we need to understand that when we get a big jump, we're going from one shell to the next shell in, and we're removing the electron from a shell which is closer to the nucleus. And secondly, we can use this to determine the number of electrons on the outer shell.